Hello. This video includes information on rate laws.
And we look at rate laws as a type of equation that helps us to relate the rates of reaction with respect to the concentration of the reactants. So this is a very generic reaction, okay? The capital letters are the reactants and the products. So A is reacting with B, and we're producing D and E. The lowercase letters are the coefficients in the balanced equation. So we've got A and B as coefficients on the reactant side, and we've got D and E as coefficients on the product side. When we look at rate laws are the concentrations of the reactants raised to some power based on how the concentrations affect the rate. And K is a proportionality constant or a rate constant. K is our rate constant. It's the proportionality constant that allows us to set the rate of the reaction equal to the concentration of the reactants. And M and N are most often whole numbers or integers. They do not come from the balanced equation. So the coefficient here in front of the A is an A, but this exponent isn't an A, it's an M. It's a different letter, different number. Okay, this is a B, this is an N. So M and N do not come from the stoichiometry in the balanced equation, but they're values that are determined experimentally based on how changing the concentration of a reactant affects its rate. Again, these exponents are typically integers, whole numbers, but they don't always have to be. I don't think you're going to see anything that's not, but they can be something other than a whole number. So if we were to look at a reaction rate, okay, a rate expression, the orders with respect to the reactants are these exponents. So A to the M power, M is the order for A in that reaction. N is the order for B in that reaction. And it tells us how A and B affect the rate of the reaction. The overall order for a reaction is just the sum of the orders for the individual reactants. So in this case, if we've got A to the M and B to the N, A is to the M order, B is N order. The overall order for this reaction would be M plus N. And we're going to fill in numbers for this in a minute. Most of the time, the orders for the reactants are whole numbers. They can be fractions from time to time. They can be zero, and that we'll see often. And they also can be negative orders, but that's not common at all. So in most cases, they're going to be whole numbers or they're going to be zero. And where do we get the M and the N values from? They come from data that's collected in experiments. So let's look at this reaction here. And we're told that experimental data shows that the rate order or the rate law is this. Okay, we're given the rate law. Rate equals K times the concentration of nitrogen monoxide squared times the concentration of hydrogen to the first power. The ones assumed to be here, we don't write those. And the brackets mean concentrations. So what is the order of this reaction with respect to each reactant? And what is the overall order for the reaction? Well, the exponents are going to tell us the order of each reactant, and the sum of the orders tells us the overall order. Nitrogen monoxide is second order. Hydrogen is first order. Okay, there's a 1 here. It's assumed to be a 1. The overall order is 2 plus 1 or 3. So let's look at this one. Okay, we've got a reaction. It gives us the rate law. And let's look at what it means. So it's second order with respect to nitrogen monoxide and first order with respect to hydrogen. Okay, so what does that mean? How will the rate change if the concentration is doubled of hydrogen is doubled? Okay, so hydrogen in this reaction is a first order reactant. That means that the concentration of hydrogen is directly proportional to the rate of the reaction. So if we double the concentration of hydrogen, that's going to double the rate of the reaction. Now, all I did, I took the rate law for the first reaction and the rate law for the second reaction. Those are supposed to be superscripts. I thought I changed that. Somehow it went back to not being superscripts. But so this is rate 1. This is rate 2, where we're doubling the concentration of hydrogen. Well, K is a constant. That cancels out. NO2 squared isn't changing, so that cancels out. Hydrogen is doubling. That's going to cause our rate to double. So first order reactants are directly proportional to the rate of the reaction. If we double hydrogen, that's going to double the rate. If we were to triple hydrogen, that would triple the rate. If we were to quadruple hydrogen, that would quadruple the rate. So first order reactants are directly proportional to the rate of the reaction. Let's say we talk about nitrogen monoxide. Well, nitrogen monoxide is a second order reactant. How will the rate change if the concentration of nitrogen monoxide is doubled? So now we're going to double this number. Okay, well, when we look at our first reaction, again, I thought these two should be superscripts. I don't know why the superscripts aren't staying there, but we're doubling the nitrogen monoxide concentration and we're holding the concentration of hydrogen constant. Again, this 2 should be a superscript. This 2 should be a superscript. So K cancels out. It's a constant. Hydrogen cancels out because we're not changing it in this question. But nitrogen monoxide is doubling. But 2 squared is 4. So doubling the concentration of nitrogen monoxide quadruples the rate. So second order reactants, whatever we do to the concentration, squared is what happens to the rate. So if we double the concentration, the rate quadruples. If we tripled the concentration, the rate would be 9 times what it was before. If we were to make the concentration 4 times, the rate would be 16 times. So second order reactions, the rate is proportional to the square of the change in the concentration. Or in other words, it's a quadratic relationship. Where do we get those rate laws from? One method of determining the rate law for a reaction, or the order for each of the reactants in a reaction, is what's called the method of initial rates. And essentially what that means is we run the experiment a whole bunch of times. we change the concentration of the reactants in each trial, and we measure the initial rate of the reaction. And then based on how the change in concentration affects the rate, we can figure out what order the reactants are. And the only way we can come up with a rate law, the only way we can figure out the order of each reactant in a reaction is by doing an experiment. It doesn't come from the stoichiometry. So let's look at some examples of kind of analyzing data and determining the order of each reactant and writing a rate law for the reaction. So here's our reaction. We've got nitrogen monoxide reacting with oxygen to produce nitrogen dioxide. Okay, we're at 25 degrees Celsius. We're not going to change the temperature. It actually doesn't have to do with these particular questions. And we're given, or we measure the initial rates of the reaction. And in this case, we run 3 trials. So here's trial 1 or experiment 1. Here's experiment 2, and here's experiment 3. So in experiment 1, the concentration of nitrogen monoxide originally is 0.020. Oxygen is 0.010. And the initial rate of the reaction is 0.028. Okay, trial 2, we hold the nitrogen monoxide constant and we double the oxygen. And we want to see, well, how does that affect the rate? And then in our 3rd trial, we double the concentration of our nitrogen monoxide and we hold the concentration of oxygen constant. And we see how that change affects our rate. So let's look at each of these reactions. Now, we're going to start by comparing trial 2 to trial 3. And the reason we're going to do that is because the concentration of oxygen doesn't change from trial 2 to trial 3. So whatever happens to the initial rate is because of the change to the nitrogen monoxide. We couldn't compare trial 1 to trial 3 because in trial 1 to trial 3, the nitrogen monoxide changes, and from trial 1 to trial 3, the concentration of oxygen changes. We wouldn't know which change causes the rate change. So we're going to look at trial 2 and trial 3. And what I would do is I would put the bigger numbers on the top and put the smaller numbers on the bottom. So I'm looking at trial 3, experiment 3, relative to experiment 2. So 0.227 divided by 0.057 is 4. So the rate is quadrupling. The rate's 4 times greater. Now, K is a constant. Oxygen is a constant. We're just going to look at our nitrogen monoxide. And we're going from 0.020 to 0.040. So we're doubling the concentration of nitrogen monoxide. We want to find out what order nitrogen monoxide is. We want to find out what N is. Well, 2 to the N power is 4. That means N equals 2, which means nitrogen monoxide is a second order reactant. We doubled the concentration and that caused the rate to quadruple. Now, let's look at oxygen. And what we can do to find out the order for oxygen is to compare experiment 1 to experiment 2. Because in experiment 1 to 2, the nitrogen monoxide is constant and the oxygen is doubling. So how does changing the oxygen affect the rate? So put the bigger number on top. So 0.057 divided by 0.028, the rate is doubling. And when we look at the concentration is doubling. So we want to find out what order is oxygen in the reaction. So 2 to the M equals 2. Well, M has to equal 1. Oxygen is a first order reactant. We doubled the concentration, and that doubled the initial rate. So we know our order for nitrogen monoxide, and we know our order from oxygen, and that comes from data. So we can write our rate law. Rate equals K times the concentration of nitrogen monoxide squared, because we decided it was second order, times the concentration of oxygen to the first, because we decided it was a first order. Now we want to calculate K. Well, K is a constant. So really all we need to do is pick one of these trials, one of these experiments, plug in the numbers from that experiment, and calculate K. Kind of manipulate the equation. We're going to divide by nitrogen monoxide squared and divide by oxygen to the first, and that's going to give us K. And we'll pick a trial. So let's just do the first trial. Okay, it doesn't really matter, but let's just do the first trial. So our rate is 0.028 moles per liter per second. The concentration of nitrogen monoxide is 0.020. I'm going to be squaring that number, but I'm also going to be squaring the units. It was moles per liter, but because I'm squaring it, it's moles squared over liter squared. And for my oxygen, I'm going to plug in 0.010. It's to the first power, so I'm just raising it to the 1, and moles per liter are going to be my units. Now, math-wise, 0.028 divided by 0.020 squared divided by 0.01 will give me my number. Now, unit-wise, I've got fractions in my denominator. To get fractions out of the denominator, I would take the reciprocal in the numerator. So if I were to take moles per liter here out of the denominator and flip it up here, it would be liters per mole. Moles cancel out, liters cancel out, and I'm left with 1/seconds. I'm going to do the same thing for moles squared over liters squared. I'm going to take the reciprocal up here in the numerator. So liters squared over moles squared over seconds squared. So my overall units are going to be liters squared per mole squared per second. And depending on the overall order for the reaction will determine what the units are for K. They're going to be different for every type of order of a reaction. So we've got 7.0 times 10 to the third liters squared per moles squared seconds. K is a constant. If we were to take experiment 2 and plug in the numbers, and experiment 3 and plug in the numbers, we'd get 7,000, 7,125, 7,093, but with only 2 significant digits, they're all exactly the same number. Okay, so our K is a constant. We can pick any one of the trials, plug in the rate, plug in the concentrations, and you can calculate K. So let's look at another example. A little bit more complicated this time because there are 3 reactants. But we're going to look at each reactant separately first and decide how does each reactant affect the initial rate. All right, so let's take a look at this one, a little bit more complicated. We need to decide which two experiments can we compare where the hydrogen peroxide changes and the other two stay constant. And then we can compare the rate to the concentration. So we're going to look at experiment 1 and experiment 2. Okay, and this is what we're trying to find. So let's look at experiment 1 and experiment 2 and see what happens to the rate. So we're doubling the concentration. The concentration of iodide is a constant. The concentration of hydrogen is a constant. The rate doubles. So if the rate doubles when the concentration doubles, the reactant is a first order reactant. So M is a 1. Now we want to figure out iodide. So we want to come up with 2 trials where the hydrogen stays constant and the hydrogen iodide stays the peroxide stays constant, but the iodide changes. So if we look at experiment 1 and compare it to experiment 3, the hydrogen peroxide is constant. The hydrogen is constant. The iodide is tripling. And the concentration is going up by 9 times. So if the rate goes up by 9 times and the concentration is going up by 3 times, we can find that iodide is a second order reactant. So we can fill that in. So hydrogen peroxide is first order. Iodide is second order. Now we want to figure out hydrogen. So let's look at experiment 1 and compare it to experiment 4. Well, hydrogen peroxide is a constant from 1 to 4. Iodide is a constant from 1 to 4. The concentration of hydrogen is doubling from 1 to 4. And we want to find out how the change in concentration affects the rate. But when we look at the rate for trial 1 to trial 4, the rate doesn't change. So 1, okay, our rate's not changing, equals 2 to the P power, which means that P has to be 0. So hydrogen is 0 order. In other words, hydrogen does not affect the rate of the reaction. So we doubled hydrogen peroxide, that doubled the rate. We tripled the concentration of iodide, that made the rate 9 times. We doubled the concentration of hydrogen, and that didn't change the rate at all. So our rate law is rate equals K times the concentration of hydrogen peroxide to the 1 power, which we don't have to write the 1, it's assumed, times the concentration of iodide squared because it's second order. And you could put in here times the concentration of hydrogen to the 0 power, but anything to the 0 power is 1. So changing the concentration of hydrogen doesn't affect the rate, and we don't have to put it into our rate law or our rate expression. And once we figure out the rate expression or the rate law, we can calculate K. So we're just going to divide both sides by our concentrations to get K by itself. Pick a trial. I just picked the first trial and plugged the numbers in. So I've got my rate divided by my concentration of my hydrogen peroxide divided by my concentration of iodide squared. Okay, I'm going to put that all in the calculator. I get 1.1 for an answer. Unit-wise, I'm going to take moles per liter out of the denominator and make it the reciprocal in the numerator, and liters and moles cancels out. And then I'm going to take the moles squared over liters squared and flip it into the numerator. And I'm going to be left with liters squared per moles squared per second. So whenever I'm asked to figure out a rate law, I'd have to be given data to do that. I'd want to figure out what order each of the reactants are, write my rate expression, and then solve for K, number and unit. So we've got nitrogen monoxide reacting with chlorine. Okay, we've got 3 trials. We vary the concentrations. We measure the initial rate. Okay, so let's look. Here's our rate law that we're trying to solve for. Let's look at nitrogen monoxide first. So in order to look at nitrogen monoxide, we want to compare 2 trials where the nitrogen monoxide changes, but the chlorine doesn't. We want to change the nitrogen monoxide, but we want the chlorine to be constant. When we look at our concentration, we're going to put the bigger one first. So 0.15 to 0.10. And our rate is going to be 0.00675 divided by 0.00300. Now, when we do that, it's kind of hard to figure out what M is this time. A little bit harder than what we did in the first 2 examples. So this is what we're going to do to solve for M, to find out what order nitrogen monoxide is when it's harder to determine. We're going to take the natural log of both sides. We can do that. It's just like taking an equation and multiplying both sides by 2. It keeps both sides equal. We can take the equation and take the natural log of both sides. Well, how is that going to help us? Well, then we can take this exponent and we can move it out in front and make it M times the natural log of 1.5. Well, how is that going to help us? Well, we're trying to find M, so we can divide both sides by the natural log of 1.5, and that will give us M. So M equals the natural log of 2.25 divided by the natural log of 1.5. And when we plug that in the calculator, we get 2 for an answer. We would have to do this if when we look at these numbers, it's harder for us to figure out what the order is. If you can't just look at this and figure out what M is, this is the path you need to go through. We figured out that nitrogen monoxide is second order. Now we want to figure out chlorine. Which 2 trials would we want to compare to figure out what order chlorine is? We want the 2 trials where chlorine changes, but nitrogen monoxide stays constant. So which 2 trials would we want? Okay, we would want to compare 1 and 2. So 0.15 divided by 0.10, that gives us our concentration. And 0.0045 divided by 0.00300 gives us 1.5. Now, this is much easier to figure out n. N is 1. 1.5 to the 1 power equals 1.5. The only time you have to do this natural log stuff is if you can't just, by looking at it, figure out what the exponent is. So nitrogen monoxide is second order, chlorine is first order. Calculate K. All right, and I didn't put it on the slide, but when you calculate K, you should get 3.0, and then your units are going to be liters squared per moles squared seconds.